Let's understand the concept of electric potential. To make this easier, I'll begin with an example you might already be familiar with: gravitational potential energy. Imagine an object lying on the ground. At this point, its gravitational potential energy is zero because its height is zero. Now, if we lift this object upwards, it gains potential energy. But where does this energy come from? It comes from the work we do while lifting the object. This gained energy is stored due to the gravitational field of the Earth. If there were no gravitational field, there would be no potential energy. So remember this important point: wherever there is a field, there is a possibility of work being done. Now let's relate this to electricity. Just like the gravitational field, an electric field can also do work. Suppose we place a positive charge in a uniform electric field. The electric field exerts a force on the charge, just like gravity acts on a mass. If we try to move this positive charge toward the positive terminal, we have to apply a force, because we are moving it against the direction of the field, similar to lifting a mass upward against gravity. So, based on this concept, electric potential is defined as the amount of work done in moving a unit positive charge from one point to another within an electric field. More specifically, we also call this concept potential difference. It is defined as the energy per unit charge when a charge moves from one point, say, point A, to another point, point B, in an electric field. This is very similar to gravitational potential difference, which is the amount of work required to lift a mass from one height to another. For example, if the gravitational potential energy at point A is 10 joules, and at point B it is 20 joules, then the difference, 10 joules divided by mass, represents the gravitational potential difference. In the same way, if a charge has 10 joules of electric potential energy at point A and 20 joules at point B, the difference, 10 joules, divided by the charge gives us the electric potential difference between A and B. There is also another important term: absolute electric potential. This is defined as the electric potential at a point when the reference point is taken at infinity, where the potential is considered to be zero. In this case, the potential difference between infinity and a given point becomes the absolute electric potential at that point. The unit of potential difference is the volt, which is defined as the potential difference between 2 points in a circuit when 1 joule of energy is required to move 1 coulomb of charge between them. Potential difference is measured using a device called a voltmeter. That's why we often refer to potential difference simply as voltage. To measure voltage, the voltmeter is always connected in parallel with the component across which we want to measure the voltage. Take a look at this diagram. We are measuring the voltage across a variable resistor. The voltmeter is showing a reading of 5 volts. Now here's a question for you. Can you figure out the value of the variable resistor that gives a voltage of 5 volts? Take a moment, pause the video and think about it. Let's solve it together. It's actually very simple. Inside the battery, there is an internal resistance of 50 ohms, and the EMF, electromotive force, of the battery is 10 volts. Now this 10 volts gets divided between the internal resistance and the variable resistor. We see that the voltmeter shows 5 volts across the variable resistor, and the remaining 5 volts must be across the internal resistance. So, according to the voltage divider rule, both resistors are dropping the same voltage, 5V each. This means the variable resistor must have the same resistance as the internal one, which is 50 ohms. If this seems a bit confusing, don't worry. We will learn in the next lecture, which is on DC circuits.